Algebra 1, Section 8.7, exponential functions. Before we get to the functions, I just want to bring up some things that we talked about earlier in the year. What if I had asked you to graph y equals 3x? We should all have an idea of what that would look like. Of course, we could make a t-chart. In Chapter 6, we did focus on slope-intercept form and, for that matter, standard form and point-slope form of lines. And certainly y equals 3x is a line. Y equals 3x would be a line that passes through the origin. And I gave you a minute there to kind of visualize what that would look like. I wanted to show it to you on my graphing calculator. This is what it would look like, right? The slope is 3. So as we go up 3, you go right 1. There's a point right there that is 1, 3. There'd be a point at 2, 6, a point at 3, 9. And there's a few points then plotted that we could draw this line had I given you some graph paper, okay? Now, there are 3, if I could pick 3, there are more than 3, but if I could pick 3 important graphs for you to walk away from Algebra 1 with, obviously lines would be one of them. Another one would be quadratics. So that's why I have here y equals 1/2 x squared. And maybe you can't visualize that one as easily as the line, y equals 3x, but yet you should be able to look at this and immediately know that it's a parabola, right? We did get exposed to this earlier in the year, and in fact in Chapter 10 we will, I don't know, based on where you are, I don't know if you're getting this before or after Chapter 10, but in Chapter 10 we focus on graphing parabolas a little bit too, and this would produce a parabola because of the x squared. And because the 1/2 is a positive number, it's going to be a parabola that opens up. Another couple of things that you might have thought of if I just asked you what do you expect to see here without actually graphing what can we expect to see, would be that it would pass through the origin. In fact, its vertex would be at the origin. There's a 0. If I plug 0 in for x, I'd get an output of 0 for y. There's a point 0, 0 on this graph. And finally, you might think of the parent graph y equals x squared and know that when you multiply by 1/2, that causes it to grow slower. So this graph would actually be wider than y equals x squared. Okay, now again, let me just give you a look at this on the calculator. Is that what you were kind of thinking? That's a quadratic, right? Now, that would be the second kind, and the third kind is what's going to be the focus today, which is exponential functions. And I'd like to start with an example. Suppose you invest $500 in an account that gives 4% interest annually. Now, again, depending on how good your memory is and what your exposure has been, you might think, hey, I wonder if this is compounded quarterly or monthly or daily or whatever. Well, that's actually the next lesson. So right now it's just annually, and compounded annually. Let's say you're making $500, or you have $500, you're making 4% on that per year. The question just is, what's a 4% increase on $500? Well, we could simply get that by going 500 times 1.04. And I do recall a discussion where we said you could take 500 and multiply it by 0.04 and get that number, which would be $20, and then add it to the original. And then we arrived at the fact that you could just multiply by 1.04 and reduce the number of steps to arrive at the same thing. 1.04 is 104%. So the answer to this is $520. In 1 year, your 500 becomes 520. Now, this is exponential, not linear, but exponential. Therefore, you would not expect it to just be $540 in 2 years, $560 in 3 years. No. It takes the previous year and multiplies it by 1.04, right? So one thing that I could do is go $520 times 1.04 to see what I would get next. And in fact, that comes out to $540.80. Not just $540, but $540.80, because you're calculating that 4% on a slightly bigger number. So you made an extra 80 cents. This is exponential growth, okay? Now, is that the only way to calculate it? No, a better way to do this, especially when we start to ask more questions like 10 years, etc., would be to do this. 500 times 1.04 to the x, where x is equal to the number of years, okay? And then to get year 0, I could just plug in a 0 for x, 500 times something to the 0 power, which is just 1, would just be 500. If I plug 1 in for x, that's 1 year later. You end up multiplying 500 by 1.04 one time, you get $520. If you plug in a 2 here, you'll get 540.8. If you plug in a 10, let's answer that question. You plug in a 10 for x, what it ends up being, and this may be a rounded number, I'm sure it is $740.12 to the nearest cent, $740.12. Okay, so this is known as exponential growth. Now, I do want to show that one on my calculator as well, so give me a moment to clear these out and type in. I know you don't have the use of a calculator, but I think this is good for understanding. 500 times 1.04 to the x. And I've already selected a window for this too. Different from the window that I typically give you on graph paper, but so that we get a good look at this. There's a look at that curve. And what this number is right here is the 500. Okay. In fact, let me even show you this feature. You'll have the use of this type of calculator next year in Algebra 2, so you might as well learn what the trace function is. See, I can trace along this function. And if I trace and then I select 0, enter, as in where we at year 0, it's at the point 0, 500. 0, 500 is this ordered pair. Okay. Now, this barely even looks like a curve, right? It almost looks like a line. You can probably see just a slight upward curve to that. But if I zoom out, that's another feature on the calculator, you can start to see a better curve there. Okay? And anyway, whether that was beneficial to you or not, here's what I want to point out to you. This equation is of the form y equals ab to the x. Y equals ab to the x. And the a is what I always refer to as the starting amount or the initial amount. That was the 500 in our previous example. And the b is what I always refer to as the growth factor or possibly a decay factor. If it's between 0 and 1, it would actually be decay. If it's more than 1, it's a growth factor. And this was growth because 1.04 is more than 1, and you know that our money was growing as we invested the $500. Okay, so what you need to know, and I guess the third thing that I'm trying to say is really important that you'd leave Algebra 1 with as far as graphing goes, is to be able to graph something like this. And we're just going to practice that 2 more times. Now, I did attach graph paper to my website in multiple places, so if you need to access that, it should be there on the page that you, possibly on the page that you access this video. Okay, and the 2 that I want to do, or one of the 2 that I want to do, one of them is y equals 8 times 1/2 to the x. We're going to graph y equals 8 times 1/2 to the x. Okay, now when it comes to problems like this, I think that there is nothing better than a t-chart. Sometimes I say do a t-chart, sometimes I say do it a different way. Here, I think that this is the best way. And for lack of better numbers to choose, I'm going to choose -1, 0, 1, 2, and maybe 3. Okay. Good place to start would be these 4 or 5 numbers. Definitely do 0, try a negative number, and then numbers that are near 0. And if you need more after that, you'll be able to add those to your t-chart very easily. All right, now here's why this is a Chapter 8 lesson. You might have looked at this discussion and say, what does this have to do with all the power rules that we were using earlier in the chapter? Here's one. What about -1 as a power? You're plugging in -1 for x. 1/2 to the -1 is actually 2. And 2 times 8 is 16. So -1, 16 would be a point on this graph. All right. If I plug in 0, another concept from early in Chapter 8, 1/2 to the 0 power is 1. 1 times 8 is 8. And then 1/2 to the first power would be 1/2 times 8 would be 4. 1/2 to the second power is actually 1/4 times 8 would be 2. And 1/2 to the third power is 1/2 times 1/2 times 1/2. That's 1/8. 8 times 1/8 is 1. And you should notice a pattern here, right? 16, 8, 4, 2, 1. That's actually a geometric sequence from a previous lesson in this chapter. And these are points that we can plot. Now, if I keep the scale that I have here, I'm not going to be able to plot -1, 16. I think I would like to do that, though, so I think I will change that. scale to go by twos. So 2, 4, 6, 8, here's 10. Then I can plot the point -1, 16. -1, 16 would be right here. 0, 8, 1, 4, 2, 2, 3, 1. Could we keep going? Sure can. And if you did 4, it'd be 1/2. And you did 5, it'd be 1/4. These are going to get closer and closer to the x-axis. They are never going to reach the x-axis. If I continued this t-chart forever, just continued to go down on this t-chart, you would continue to get positive numbers, just smaller and smaller, that are closer and closer to 0, but they would continue to be positive numbers. Anyway, you don't need to do that. In fact, you can see, hopefully you can see what the pattern is approaching. So we want to do the best we can. And this is not art class, and this is a little bit difficult for me to do on this screen, but we want to show what this function is doing in both directions, right? Show that curve, use arrows to show that it continues in those directions, and definitely make sure that in this space right here, you don't have something that coincides with the x-axis or crosses the x-axis. That would basically demonstrate that you don't have full understanding of what these do. This is going to continue to get closer and closer to the x-axis, but stay in the first quadrant, okay? So that was y equals 8 times 1/2 to the x. Now we called this earlier, we called this decay. Why? Well, you can tell by the graph that as x gets bigger, the graph is getting smaller. The y values are getting smaller. And the thing that's controlling that is the 1/2. Something between 0 and 1 in the b position is going to cause this to be exponential decay. The other one that I want to do is y equals 3 times 2 to the x. And again, we'll make a t-chart. And notice on my graph here that I don't have a scale, and I'll wait on the scale a little bit of time here just to see what happens. But let's start with the same 5 numbers and just see what goes on. 2 to the -1 is 1/2, right? Move it and lose it. 2 to the -1 is like saying 1 over 2 to the 1, that's 1/2. Oh, sorry, and then we're going to multiply by 3, so that'd actually be 3/2. 2 to the 0 is 1, times 3 would be 3. 2 to the first is 2, times 3 would be 6. 2 squared, 4, times 3 is 12. 2 to the third is 8, times 3 is 24. Again, notice the geometric sequence that's occurring in the y column there. If you wanted to go further into the negative, you could, right? If you put a -2 here, that I didn't leave myself any space for it, so I have to point at it with arrows. 2 to the -2 would be 1/4, times 3 would be 3/4. That's probably good right there. Those 6 numbers will be good to plot. And I think just like the last example now, I'll go by 1s on my horizontal scale, and I'll go by 2s on my vertical scale. That way I'll have just enough space to put that 324 in place. And plotting points, we had -2, 3/4, which would be right about here, right? Remember that this is 2, so this is 1, so about 3/4 would be right about there. -1, 3 over 2 is 1.5, so right about here. 0, 3, 1, 6, 2, 12, and 3, 24. And again, this would continue to the left. If you continue to put in bigger negative numbers, it would stay in the second quadrant above the x-axis. I had a college professor once who liked to use the word infinitesimally, meaning that the distance between our curve and the negative x-axis would continue to get infinitesimally small, right? So again, I'm doing the best I can on my screen here to show that, and it did stay above the x-axis. The arrow says that it would continue in that direction. And just to close this up then, this is exponential growth because as x grows, our graph is growing up, right? And the thing that controls that is the 2, the fact that 2 is greater than 1. 1 is the cutoff. If anything's bigger than 1, it's going to be growth, as you see here. If it's something less than 1, between 0 and 1, it would be decay. Thanks for tuning in.